we have finally come to the actual exercises from the text. So in this first one, we are given some groups and some functions defined on those groups. We have to decide whether each function is an automorphism of the given group. So in the first part, the group is the group of integers under addition, and the function t maps every integer onto its negative. The map, of course, is well defined. For any two integers x and y, we have, keep in mind that the operation now is ordinary addition of integers. The t image of x plus y is minus of x plus y, which we know is minus x plus minus y, and this is xt plus yt. Hence t is a homomorphism. So the next thing we now have to see is whether t is one-to-one and or onto. For two integers a and b, if at is equal to bt, then minus a is equal to minus b, because at is minus a and bt is minus b, and so a is equal to b. Thus t is injective or one-to-one. One can also see that t is onto, but just for the sake of this solution, we show that also. Next, or we can write also, for any integer n, we have the integer minus n such that the t image of minus n is n. Thus t is onto. So t is a homomorphism that is both one-to-one and onto. Hence t is an automorphism. So this is part A. Then in part B, the group is the group of all positive integers under positive reals under ordinary multiplication, and this is the function. This function is also well defined, just like the previous one. For two positive real numbers x and y, we have, now the operation is multiplication of reals. The t image of xy is the square of xy, which we know is equal to x square times y square, and x square is xt, y square is y, t. Hence T is a homomorphism. Now next thing we will show is of course just what we did here. T is 1 to 1 and then T is onto. Now this one-to-oneness, instead of showing directly like this as if you were showing that a function is one-to-one, you can also use, since T is a homomorphism, we have proved that you can use the kernel criterion to show that T is one-to-one. Namely, if you are able to show that the kernel of T consists of only the identity element in the group, then automatically T is one-to-one. So for a change, here we show one-to-oneness of T like that. Now let A belong to the kernel of T. Recall that KT denotes the kernel of T. Then the T image of A is the identity element in the group. Since we have the multiplicative group of positive reals, so the identity element is 1, the real number 1. But according to the definition of T, AT is also A square. So A square is 1 and A is a positive real number. Note that because we are assuming A to be in KT, where KT is the kernel of T. So KT is a subset of the given group. In fact, it's a normal subgroup of the given group. So A after all is a positive real number. Since A is positive, we must have A equal to 1. The other possibility that A is minus 1 does not occur. So the kernel of T consists of this single element. This implies T is injective or one-to-one. Okay, now next we show T is onto. Let B belonging to G be any element, that is B is a positive real number. Now, since B is a positive real number, we know from real analysis that there is something known as the positive square root of B. Such a real number exists, which is when you take the square of that real number, you get B back. Then, and we denote that real number by this familiar symbol. The T image of square root of B is B. So T is a homomorphism, it's one-to-one and it's onto. Hence, T is an automorphism of the given group. Okay, next C. Here G is a cyclic group of order 12. Let cyclic group means it will be generated by some element where A is an element of order 12 in G. Okay, we need to see whether this is an automorphism. Now this turns out to not be an automorphism. See, an automorphism demands three things. It should be a homomorphism, it should be one-to-one, and it should be onto. If any one of these three things is not true, then it's not an automorphism. In this case, this function is not one-to-one. Let's see why. Note that this of course belongs to the fourth power of the generator A. This is clearly not equal to identity. Why? Because A has order 12. So 12 is the smallest positive integer such that A to the power 12 is equal to E. No smaller exponent will give us E. And this such that but E is also ET. So two different inputs but the same output of them under T. This shows that T is not one-to-one and hence is not an automorphism. Finally, in part D, G is our familiar group S3 and the map T maps every element onto its inverse. This will also not be an automorphism for a different reason than the previous one. It's not a homomorphism. Let's see. Note that phi and psi belong to S3. If you want to recall what phi and psi is, they are these maps on the set consisting of the three symbols 1, 2, 3. They are bijective maps on this set. Phi maps 1 to 2, 2 to 1 and 3 to 3, and psi maps 1 to 2, 2 to 3 and 3 to 1. Okay, so both of them, as you can see, are bijective maps on the set 1, 2, 3. So they belong to the symmetric group S3 of degree 3. Okay. Such that now what happens when we apply our T to the element phi psi? Phi psi, if you go back to the description of the elements in S3 that we saw back then when we were studying groups and their examples for the first time, there you will see that this is an element whose inverse is equal to the element itself. Because the square of this element is identity. But if we calculate this instead, then we get phi inverse psi inverse. Now phi inverse is phi. Phi is an element like phi psi. The inverse of phi is also phi itself, and that comes from the fact that phi square is identity. But psi is not such an element. Psi square is not identity. Psi cube is identity. Because of that, psi inverse is psi square, and these two things are not equal. Had they been equal, psi would have been equal to the identity by the cancellation laws, which is not true. That is, not equal to so T is not even a homomorphism here. Homomorphism, and hence is not an automorphism. So this completes the solution to the first one. Okay, then in the second one, let G be a group H a subgroup of G and T an automorphism of G. Let HT be the set of all elements in G of the form HT as H belongs to H varies over A. That means HT is just the image of the set H under the map T, ordinary image. Proof this is a isn't it something we already know? In a much more general setting, if we say we have two groups G and G prime, and say phi is a homomorphism of G into G prime. Phi need not be an automorphism, and it also need not be even onto. Then the image of G under phi, the same thing HT, is a subgroup of G prime. In fact, we have proved this, and for the proof, you see lemma 275. Then in exercise 3, a similar one, but now instead of an ordinary group, we have a normal subgroup. Let G be a group. That also is taken care of by this same lemma. T an automorphism of G in a normal subgroup of G. This lemma, if you are wondering what this lemma is, this is that correspondence lemma which tells us that if we have a homomorphism from one group G1 onto another group G2 with some kernel, then there is a one-to-one correspondence between the subgroups of the second group G2 and the subgroups of the first group G1 containing that kernel. And under this one-to-one correspondence, normal subgroups correspond to normal subgroups. So that part will be used here. Then prove that. So whatever we need to answer these two exercises are already available in this lemma. NT is a normal subgroup of G. Here also same, C lemma. Two, 7, 5. Then 4. for G equal to S3 prove that G is isomorphic to the inner automorphism group of G. Since the center of S3, or let us write G itself, G is the trivial group, which you can verify. The center of S3 is the trivial group. There is no element in S3 other than the identity that commutes with all the elements of S3. So the center is trivial, hence we started with since. So what is that result? Lemma two 282 implies this is isomorphic to this, which itself is isomorphic to G. It is that result which says that the inner automorphism group of any group is isomorphic to the quotient of the group by its center. You recall this result? From that we directly get the thing. Then exercise 5. For any group G, and this one is very interesting. Prove that a group of inner automorphisms of G is a normal subgroup of the automorphism group of G. We already know, we have shown that this is a subgroup of this. This has all the automorphisms of G, this has the inner automorphisms. But now we are asked to show that in fact this is normal in this. So once we show that, one can then form the quotient of this by this normal subgroup, and that group has a name. The group is called the group of outer automorphisms. Okay, so let us now show the normality. We already know that this is a subgroup of the automorphism group of G. Let us take two elements G and H belonging to G and any automorphism S of G. We will see why we have taken G and H. Then H S inverse TGS. So what we are doing, from this G we will get an inner automorphism, namely the inner automorphism corresponding to G. So we have TG, which is an element here, and S is any element in the larger group. So we have formed this product S inverse TGS to show that IG is normal in AG. It's enough to show that S inverse TGS is again in IG. That is, this is again an inner automorphism. But we cannot directly work just with this. We have to see what this function does to an arbitrary element of G. So that's why we have to take another element H. Okay. So now, since the operation in this group AG or IG, this is function composition. So this gives us HS inverse TGS. Okay. Now HS inverse TGS, HS inverse TGS. Now this gives us G inverse HS inverse G S. Here in this step we are just applying the definition of TG, because TG maps any element to G inverse that element G according to the definition of the inner automorphism TG. Okay. Now S is an automorphism, means S is a homomorphism. So if we apply S on this product, because it's a homomorphism, it will get distributed. Now again, because S is a homomorphism, applying it on G inverse is the same as the inverse of GS. From the elementary properties of a homomorphism, and this, if you see, will give us H, because S inverse S is the identity automorphism, so that is H, and we have GS here. Now note that GS is after all an element of capital G, because we have applied the automorphism S on G, so we are going to get an element in G. And now looking at the final form of this product, you can see that this is nothing but HTGS. But since we chose H to be an arbitrary element of G, so these two functions, this one and TGS, have the same effect on every element. Thus, S inverse TG S is equal to TGS, and that's why this belongs to IG. This shows that this is normal in the automorphism group of G. This equation is very beautiful, this one. Then exercise 6. In the 6th exercise, we are given a specific group. We are asked to determine its automorphism group. Let G be a group of order 4. I don't know why the author says a group of order 4, because the group itself is given. And AB is equal to B. Oh, so in that sense he says a group of order 4, because we just need these facts about the group. We don't need the fact that G is unique, that is, it is the only group of order 4 satisfying these properties. That is not needed. Determine the automorphism group of G. I think I will never learn to write this A properly. We are going to concentrate on two maps defined on G. Define a map A from G to G by these formulas. EF is defined to be equal to E, then AF is defined to be equal to B, BF is defined to be equal to A, and ABF is defined to be equal to AB. And another map, G also from G to G, by these formulas. EG is equal to G, then AG is B, BG is defined to be equal to AB, not A now, and ABG is defined to be equal to A. Now the thing, this you have to do, one can verify that F and G belong to this. That means F and G are automorphisms of G. For that you have to, for example, if you want to show that F is an automorphism, first you show that F is one-to-one and onto, which you can see pretty easily from the definition of F. And then you have to show that F is a homomorphism. This is true, and this is also true for G. F and G are both automorphisms of G. Okay. Note that what is the FG image of the element A? First, if we apply F to A, then AF is B. On that B, if you apply G, then BG is AB. And AB is not equal to A. And A turns out to be the GF image of A. Let's see. AG is what? AG is B, and on B if we apply F, BF is A. So that means this is A. That is, FG is not equal to GF, because the functions FG and GF give us different elements, different outputs at the input A. So they are not equal, and since they are automorphisms, so this automorphism group is not abelian. Thus, this is not abelian, since every group of order at most 5 is abelian and this of course we have already solved in an exercise C. Exercise 9 of section 2.3. So because of this, we must have order of the automorphism group greater than or equal to 6, because it's non-abelian, so it must have at least 6 elements. Let us now think about how big this can be, and that is because we have, you see, what are the elements in this? The elements in this are bijective homomorphisms on G. Now, if we look at the elements of G, E, A, B, A, B, E, A, B, A, B. If F is, F means, don't confuse that with this F. Okay, let me say something else. Say H is or T is an automorphism of G, then because T is homomorphism, E must be mapped onto E, and because T is onto, no other element gets mapped onto E. And in fact we can just simply say, not just I said T is onto T, because T is 1 to 1, no other element gets mapped onto E. Or we can directly say this: since T is bijective and the image of E must be E, so this is only the place where things can change. That is, for example, if your T is the identity automorphism, then A gets mapped onto A, B to B, AB to AB. But if your T is this F, then A gets mapped onto B, B onto A, and AB onto AB. Whereas if your T is G, then A gets mapped to B, B gets mapped to AB, and AB gets mapped to A. So how many different possibilities can there be? What do you think? This is fixed, so we are able to consider mappings which are bijections of these three symbols. So that means 3 factorial. So there can be at most 3 factorial or 6 automorphisms. In fact, at most 6 bijective maps that satisfy this extra condition that E must get mapped onto E. So we can write like this: since any automorphism of G maps E onto E, and there are 3 factorial equal to 6 permutations of the symbols A, B and AB, we have this. We are not saying that all the 6 functions that you get as bijections satisfying that E gets mapped onto E are automorphisms. That's not what we are saying. We are saying that that is the maximum number, because that many bijections you have. So some of them will be automorphisms like F and G, and some of them will not be automorphisms. So now you combine these two inequalities. So order of this must be equal to 6. Hence, order of the automorphism group of G must be equal to 6. So that means A of G is a group of order 6 that is non-abelian. So we can now use that exercise that we have already seen. So by exercise 7 of section 2.7, the previous section, the automorphism group of G is isomorphic to S3. There is only up to automorphism up to isomorphism there is only one non-abelian group of order 6, that is S3, that we have already proved in this exercise. So this is a non-abelian group of order 6, so it must be isomorphic to S3. Isomorphism means you have found actually essentially what the automorphism group is. And this is something extra. Here the given group G is isomorphic to J2 cross J2. To understand what this cross is, this is direct product, you have to see the last section 213. We will see these things. And J, don't forget, J is the symbol that represents the set of integers. So the more familiar notation is this. So this is the solution. Then seven A. A subgroup C of G, where G of course is a group, is said to be a characteristic subgroup of G if the T image of C is again contained in C, and that too for all automorphisms. For all automorphisms T of G. Okay, this is a very stringent condition. This should be true for all automorphisms T of G. But in spite of this very restricted condition, characteristic groups, subgroups exist. Two trivial examples can be immediately thought of. G itself is of course a characteristic subgroup of G, and also the trivial subgroup consisting of the identity element, that is also a characteristic subgroup. So these are trivial examples. Prove that so this is a necessary condition for a subgroup to be a characteristic subgroup. Prove that a characteristic subgroup of G must be a normal subgroup of G. part B, prove that the converse is false. Every normal subgroup is not a characteristic subgroup. Understandably, because the condition for a subgroup to be characteristic is much stronger than normality. Something has to happen for all automorphisms. Okay, let C be a characteristic subgroup of G. Let G be any element in G and H be an element in C. Then if we apply the inner automorphism TG on C, then the image will be contained in C because C is a characteristic subgroup. This implies G inverse HG, which is the TG image of H, will belong to C because H is coming from C. Since this image is contained in C, so the image of this single element from H will be contained in C, which is G inverse HG. So see what we have proved. G is any group element and H is any element in C. So G inverse HG belongs to C. Hence, C is normal in G. So every characteristic subgroup is normal. Now the converse is not true. Luckily, the group that we have seen in the previous exercise, that this one, is the group where we can get a counterexample. Let G be the, in fact, let us just also show the elements E, A, B, AB, be the group from exercise 6. The cyclic subgroup generated by A is normal in G because its index is 2. G is a group of order 4, and since A itself is an element of order 4, so this cyclic subgroup has order 2. So the index of this subgroup in G is 4 divided by 2, that is equal to 2. And we know that if a subgroup in a group has index 2, then it is normal. So that's why this cyclic group is normal. But this is not a characteristic group. To see why, we need an automorphism under which the cyclic subgroup does not get mapped onto itself, and the function f that we saw in the previous solution, that is such an automorphism. Let f be the automorphism in the solution to exercise 6. We have A belonging to the cyclic subgroup generated by A, but when we apply the function f on A, we get B, which does not belong to this. Hence, this is not a subset of this. So the condition that A gets mapped onto itself, into itself by every automorphism fails here for this particular automorphism. Thus, this is not a, let me just see for a moment, if A is actually equal to B, I mean AF, yes, AF is B. So this is not a characteristic subgroup of G. So that completes this solution. After this, there are other exercises which we will solve in the next video. I think there are 21 of them in total, out of which we have solved so far 7. So we will see the others in the next part. Tomorrow we have calculus, no? I think there is calculus tomorrow. Anyway, so until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.